me remind you that last time we talked about window package and we've seen suitability. It can solve for us more or less whatever problem we give it in your programming problem. And we realized that for this task of solving a complicated problem, the most we can do is formulate the problem in a way that will be easy for us to understand, to change some parameters, and then just give it a window and see what the answer is. And last time I tried to discuss an example of a somewhat complicated problem, and we tried to formulate it. Let's start from more or less from scratch. I'll remind you what the problem is and you'll see how to formulate it. So the problem was the following investment problem. Every day, you can invest X dollars, match by half of X dollars next day. And get $2 at the beginning of the third day. So somehow we have the following opportunity. Every day, say on Monday, you can invest X dollars, let's say $100. The next day you must match this investment by another investment of half of this sum, so in this case $50. But then on the third day, which is Monday, Tuesday, Wednesday, beginning of Wednesday you'll get 2 times the initial investment, which means $200. And the question is, if we start on Monday with $90, so suppose you start with the total amount of money which is $90, how should we invest? To maximize to get the largest amount of money on Sunday. So that was the problem. We want to find an investment schedule which will maximize whatever you get by Saturday. And last time we talked about the assumptions hidden in this formulation. For example, if you invest something and you do not match it by half of this investment the next day, you just lose this money, so there's no sense in which it's good for you to invest something and not match it by something the next day. You can't go kind of overdraft, you can't borrow money, you can't spend more than you have. And last time we started to discuss how to formulate this question as a linear programming problem. So first of all, we decided on some parameters which are just necessary for this formulation. What were those parameters? These were the parameters which you want to get as your answer. If you want to know how to invest every day from Monday to Saturday, you'll want to have the parameters which tell you, well, invest such and such amount on Monday, such and such amount on Tuesday, and so on. So we set the parameters. At the very least, should include the following. Xi will be amount to invest on day I. So on Monday, we will invest X1. On Tuesday, we will invest X2. So at least, if we have these as parameters, once we get the answer, it will include this number. So that's good. Also, it seems that these parameters are enough for our formulation. If we know how much we invest each day, well, we know what happens. We know whether we go overdraft, we know whether, well, what is the amount that we get on Saturday. So we should be able to formulate this problem entirely with these parameters only. And last time we started this, but we had kind of little time. So let's do this. Let's try to formulate what happens with our investment and see what we are trying to maximize, what are the conditions, what are the constraints. So I'll do this as follows. Thursday, Friday, Saturday. So each day I will write down, well, the amount of money we start with, the amount of money we invest, the amount of money we use to make the investment from previous day. What else? We can get some money, and we can end up with some amount of money on that day. So we'll try to fill in this table. So on Monday we start with $90. We invest X1. That's the amount of money you invest on Monday. You don't have to make any investment. You don't get anything. And, well, you end up with 90 minus X1 dollars. So that's how Monday went by. We started with $90, invested X1, ended up with 90 minus X1. Our Tuesday starts with, well, whatever we got from here, 90 minus X1. Then we invest some amount of money, which we denoted as 2. Then we match this by this amount. So it should be, now it's not an independent number, it must be exactly half of the investment amount. So this should be X1 over 2. We will get 2 times, oh sorry, this day we still don't get anything. We'll only get our first return on Wednesday, so we still get 0 here, and we end up with 90 minus X1, minus X2, and minus another half of X1. So minus 3 halves of X1 minus X2. Okay, in this table, some entries are quite easy to fill, well, from the beginning to the very end. For instance, these amounts, how much we invest, well, we just know what they are. They are X1, X2, X3, X4, and so on. So let me do this. X3, X4, X5, and X6. We match those amounts by half of the investment on the previous day, so it's also very easy to write down. X2 by 2, X3 by 2, X4 by 2, X5 by 2. The amount of money you get on this day is, well, twice the investment 2 days before. So here it will be 2x1. Here it will be 2x2, 2x3, 2x4. These amounts are, well, a little more complicated. So we can't really see that what this will be, and then write what this will be, and this will be, and so on. We'll have to do it step by step. So we know what we ended up with on Tuesday. We'll start Wednesday, well, not quite with the same amount, because at the beginning of each day we get the investment when we get the return from investment 2 days before. So we'll start with this amount plus this return. So this and this together give you this amount. So this and this together will give you 90 minus 3 halves and plus 2. So plus x1 by 2 minus x2. Then, once you know what you started your day with, you can use these and the amount that you invested, that you used on this day, to get to the amount that you end the day with. So it's 90 plus x1 by 2 minus x2 and minus these things. So it will be 90 plus still x1 over 2 minus x2 and minus x2 by 2, so minus 3 halves x2 plus, no, minus x3. Okay, so already here it gets a little complicated, but let's continue this, okay? So we end up with this amount on Wednesday, then we start Thursday by this amount plus the investment that we get on Thursday. So we take this amount and add to x2, so we get 90 plus x1 over 2 minus 3000 plus 2 of x2, so plus x2 by 2 minus x3 minus x3. Then you take this amount and you use x4 and x3 by 2. So you invest x4 and you match the investment from the previous day x3 by 2. So you subtract from this amount these investments, you'll get 90 plus x1 by 2 plus x2 by 2 minus 3 halves of x3 and minus x4. So now we have all Thursday. We start with this amount on Friday, but then we get the investment of 2x3. So it will be, okay. Now we have to squeeze these expressions tighter. They get longer and longer. Plus x1 by 2 plus x2 by 2 plus x3 by 2 minus x4. Then we'll take this expression and subtract this and this. Maybe we can save ourselves a little bit of space by realizing that this investment on Friday is actually not quite necessary. So think about it. What happens to this investment on Friday? You will have to make it with half of this investment on Saturday, and you'll get the return only on Sunday. So it won't be reflected in any way in the amount of money that you get on Saturday. I mean, it will be reflected, but only kind of what you gave up. So this can be assumed to be 0, and this can be assumed to be 0. And of course, you don't want to invest anything on Saturday. You just want to maximize the return on Saturday. So this is also 0. So now it's a little bit simpler. You take this amount and you only subtract this thing to get to 90 plus x1 by 2 plus x2 by 2 plus x3 by 2 minus 3 halves of x4. Then you start Saturday with this amount plus the return on Saturday. 90 plus x1 by 2 plus x2 by 2 plus x3 by 2 plus x4 by 2. And you end up with the same amount. So this is the same. So now we have full understanding of what happens each and every day from morning to evening, and we can write down what is our linear programming problem. We want to maximize the return on Saturday, so we want to maximize this number that we get by the end of Saturday. Maximize 90 plus x1 by 2 plus x2 by 2 plus x3 by 2 plus x4 by 2. Subject to the constraints. Well, what will be the constraints?
Is it all your investments and all your end values are greater than or equal to 0?
Yes, exactly. So my constraints are, I want to invest only positive amounts, I don't want to borrow from anyone, and by the end of the day, after I make all my investments, I want to get non-zero, non-negative amount of money. I don't want to go over that. So my constraints will be 90 minus x1 greater or equal than 0, 90 minus 3 halves x1 minus x2 greater or equal than 0. This amount, 90 plus x1 by 2 minus 3 halves x2 minus x3 greater or equal than 0. 90 plus x1 by 2 plus x2 by 2 minus 3 halves x3 minus x4 greater or equal than 0. This amount, 90 plus x1 by 2 plus x2 by 2 plus x3 by 2 minus 3 halves x4 greater or equal than 0. And also this amount is greater or equal than 0. This is not as important. It will be automatic if the investments are all positive, as you see. Now let's add it. And of course, x1 positive, x2 positive, x3 positive, x4 positive. Well, these constraints are not quite in standard form. They involve both numbers and variables on the same side, and the inequality signs are not quite what we want, but it's easy to correct. Of course, we can take this 90, so we can write it here, x1 is at least 9, it is at most 90, 3 halves is x1 plus x2 is at most 90, and so on and so on. So if you wish, you can translate those. So x1 is at most 90, 3 halves of x1 plus x2 is at most 90, and so on. So this is a formulation of this problem. But I want to say that I would discourage you from using such kind of formulations. Well, in general, even in this kind of problem which I use just for the lesson, but usually problems get much longer, and this kind of formulation is terrible. So what happens here, you can't really, well, first of all, if you make some small mistake, say here you copied this amount and turned out that you, instead of -1, wrote -2, or forget about it, the minus wrote plus. It becomes quite impossible to track down where the first mistake is. It's a mistake in formulation, I remind you. So even after you get solution and you see that it's quite wrong, that you get some numbers which are not reasonable at all, it still will be hard to understand where was the problem. So that's one drawback of such kind of formulation. Another one, let's say you want to introduce some variations on the problem. Let's say you can get interest on the remaining balance in the end of the day. If you end up the day with say $10, you can invest it overnight and get 1% of your investment by the next morning. How will it change the formulation of this problem? The answer is, it will be awful. You'll have to take, say, this balance, multiply this number that you start the next day by 1.01, so add 1% of this amount. This will have effect on this amount, then you'll multiply this by 1.01, it will have kind of double effect on this amount, and so on. So by then, when you get to this amount, you are more or less guaranteed to have made some mistake. So in this sense, it's also, well, not really good. Maybe well, if you want to change some parameters in your program, if you have to make the investment not by 1/2 of x2, but of x by 1/3 of x, how does the problem change? Once again, you'll have to track what happens at each of these steps, which numbers get changed to which numbers. By the end of the whole procedure, once you get to the final expression, once again, it's quite likely that you will make a mistake. So this formulation, well, it is correct. I mean, technically it is correct. But it's not robust to any kind of changes, any kind of changes in parameters, changes in problem. It's not even, well, I would say it's not even understandable to a human. I mean, yes, you can start with this formulation and translate it to this formulation, but once you see this formulation, it's not quite obvious how each of these lines correspond to each one of these things. So why this number is somewhat important. Not understandable at all. So what I want to do now is write down a better formulation of the same problem, which will show, well, kind of an important trick. So the new formulation will exploit the fact that some of these numbers, first of all, they are meaningful to us. So each one of these numbers has some meaning. It's the amount of money that you get by the end of the day. And also in the formulation of this problem, it seems like, well, you don't really have to know, to get this number, you don't really have to know all the numbers in this table. You only have to know what you ended up your previous day with, and what you invested on this day, and what you got on this day. So it's not that this number depends on the whole table. It only depends on what you already have here. The problem with our formulation was, well, we had few parameters, and somehow changing each one of these parameters had an influence on the whole table. So somehow this whole table, well, as you move to the right, it becomes more and more dependent on everything which happened to the left. On the other hand, the actual thing that the actual problem, well, it has some kind of locality. This information only depends on this, and this, something like this. So we'll rewrite this table: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. But now we will use the following: start, invest, match, get, and end. Well, we'll start our day with some amount of money, but once again, I don't want to express it in terms of these parameters. Similar to what I will do with investments, which I'll call just x1, x2, x3, x4, x5, x6. I'll just write down what are the amounts that we start with on each day. I'll call them, well, M1, M2, M3, M4, M5, M6. Of course, I do know something about these amounts. I know, for example, that M1 is 90. Okay, for now, let me leave it as it is. What happens with the amounts that we match the investments by? Well, I'll have just the same line. On each day I invest, I match the investment from the previous day. on each day I get twice the investment of 2 days before. So 2x1, 2x2, 2x3, 2x4. So there is no problem here. What happens at the end of the day? Well, I could write down in terms of these numbers what is the end of the day, but let me, well, kind of push this idea of introducing extra parameters to this limit. Let me say that I end up with E1, E2, E3, E4, E5, E6. Okay. Of course, not all these numbers are independent. If I know what is M1 and I know how much I invested on the first day, I know how much I get at the end of the day. So I can write that E1 is in fact what I started the day with minus x1. Well, what about E2? Well, it's what I start my second day with, and 2 minus what I invest on this day, x2 minus x1 by 2. In fact, this kind of constraint will get repeated once again here, 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 and here. So E3 is just what I start the day with, minus what I use for investment, minus what I use for matching. Exactly the same form. E4 is M4 minus X4 minus X3 by 2. E5 and then E6. So E5 is something and E6 is something, and this something has exactly the same form. So in general, the pattern is like this. What you end the day I with is what you started with, minus the amount that you invest on this day, and minus half of the investment of the previous day. Well, of these things, there is only one constraint which looks a little bit different. This one, the first one, and the reason is, well, right here. This should have been kind of x0 by 2, but x0 is of course 0, because we don't have any investment on the previous sum. So in fact, this constraint is also this form, it's just that x0 is 0. Okay, another thing. How do we know what we start our day with? For now, we just said that if we know what we start our days with, we'll also know what we end the days with. But also we can know what we start the day with. What we start on the second day with is, well, what we end the first day with, plus the amount that we get from investment. So we get such a thing. M2 is E1 plus, well, in this case 0. And for all other days it will be M3 is E2 plus 2x1. M4 is E3 plus 2x2, and so on. The general pattern, once again, is what you start the ice day with is what you end up on the previous day plus 2 times the investment 2 days before. And once again, even the first one here is about E1 plus, it should have been 2x0, but x0 is 0. Okay, so in this case, our constraints are kind of equalities. And what's good is, it's really easy, once you have these constraints, to understand, well, what is our problem. In fact, I can squeeze the problem formulation right here. It's now so compact. What I want to do? I want to maximize E6. Subject to what constraints? Well, all the numbers should be positive. So I should end up on each day with positive amount. I should start with positive amounts. I should invest with positive amounts. subject to, well, I is positive, xi is positive, and I is positive. So everything is positive. So let me replace this formulation, which is not really good, with this new formulation. It is much, much better. Instead of, well, lots of ununderstandable constraints, like these ones, I basically have, well, I don't just have a small amount of constraints, I still have lots of constraints. I even have lots of parameters now. But what's good is all the constraints look more or less the same, either this form or that form. If I want to change some parameter in my problem, let's say I want to measure my investment not by 1/2 of the investment on the next day, but 1/3, well, change basically just one number right here. If I want to introduce some interest rate, well, instead of saying that the next day starts with what you ended up the previous day minus plus what you get, well, multiply this amount by whatever you get with the interest rate, 1.01. So this formulation is much, much more robust, much, much more understandable. So we'll use this second formulation to, well, to ask our computer what is the answer. Before we do so, any questions? Well, connect the projector.
I have a question about implementing that with computer. So can you just give that little form and I minus xi, should I like
So
have it as a loop or all I be doing in Lambda?
So people who know how to program will say that, I mean, yes, you should actually not repeat all the constraints one by one, you should just write some kind of loop over all the constraints, and there is a way to do this, but Lindo itself doesn't do this. There is a kind of programming language associated with Lindo, it's called GameGo, and it can loop over constraints, and it's kind of specifically designed for formulation of such kind of problems. Or, I mean, if you know how to program in any language, just write down a simple program which generates such expressions and copy the output. But Lindo itself doesn't know how to do this, so we have just to copy it. So we open Lindo and turn off the lights. Increase the size of the point, so then we'll start implementing this. So first of all, I want to maximize the amount of C6. Subject to, and now we have some constraints. So between subject to and end, I'll have some constraints. And what are those constraints? Let's start with these constraints, which define what is EI. So first constraint is E1 is equal to M1 minus X1 and minus 1/2, which I will write as 0.5 times x0, which is 0. Okay, so one comment about this thing. my program will not be able to run if I write it this way. I mean, if you try to solve it, it will say expecting the right hand side value, the following was interpreted, and so on and so on. So what happens here, Lindo expects every constraint that looks like some linear combination of variables is, well, some sign, equality or inequality, and then a number. So you can't write down such a constraint, but you can write down such a thing. E1 minus this expression is equal to 0. So this constraint is a well-formed expression in Lindo. And then we'll basically want to duplicate it 6 times. So before I go on with writing down these constraints, I said something about x0 being 0. So let me write down the constraint that x0 is equal to 0. And also let me give some names to these constraints. So x0 is equal to 0 is no investment on Sunday, on previous Sunday. And the second constraint is about the end of day 1, maybe evening of day 1. Evening of 1. I'm not using the name of this constraint as end of day 1 because somehow Lindo interprets the word end as a keyword. So there is no way to use end. Now copy this 6 times. 1, 2, 3, 4, 5, 6. And just change the numbers. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Plus 2, 3, 4, 5, 6. And 0, 1, 2, 3, 4, 5. Yeah.
Does Lindo allow looping expressions so that you can use I and instead
So,
of writing it?
as I said, unfortunately, Lindo itself doesn't. There is a programming language. I mean, you can connect Lindo to what's called Lingo, which can loop over things and it can kind of connect to a large Excel table from which it can pull out the data. So there is a more powerful language in Lindo. Lindo itself is just, well, just the solver of linear programming problems. So there is a language that uses this Lindo to solve linear programming problems, but it is an actual programming language rather than just solver, but we won't go there. So as I said, if you encounter a really large problem with this kind of thing and you don't want to copy, of course copying is no error problem, you don't produce errors. So either learn the programming language Lindo or use whatever language you already know and generate these expressions as output. Okay, and then we want the constraints about the mornings. So these types of constraints. So morning 1 will be about the amount on the first morning, being the amount on the previous evening. Okay, sorry. So first morning is somewhat exceptional. First morning we just know what is the answer. First morning we have $90. It's just given. On second morning it will be closer. It will be second morning is what you ended up in the previous evening, plus 2 times, so minus 2 times x 0. So that second morning and all other ones should be the same. So I copy this 2, 3, 4, 5, 6. 3, 4, 5, 6. 2, Okay, so I wrote down this thing. Now I know, so I have a way to know if I know my investments, which are the parameters. One of them is 0 on the very first day, on Saturday, the minus first day. The other ones should be determined. I start my first morning with $90, and then I know what will happen on the second morning. Well, first of all, I will know what will happen the first evening, second morning, second evening, third morning, and so on. So it seems that I define everything. And besides these definitions, do I need any other constraints? Well, unless I forgot something, the answer is no. The other constraints are just positivity constraints about the variables. So Lindo, as I said, automatically assumes that all the variables are positive, so I don't have to write down any of the constraints. If I wrote it, I would write the constraints that each one of these numbers is positive. I mean, if I had to write it in actual standard form, but here I don't. It automatically assumes that they are all positive. Okay, and now we get to kind of debugging our model. If it is correct, we'll get some reasonable answers. If it's not correct, we'll get something wrong and try to see where the problem is. So I hope it is right, but you never know. So it tells us after 8 iterations, so after somewhat long process, we did find the optimal solution. The objective function is 187.3. And let's see what kind of schedule we get from this. So objective function is this thing, which is what you end up in the 6th evening, which is good. The investment schedule. So x0 amounts that you invest. x0 is of course 0. That's the amount that you invest on previous Sunday, which is 0. We asked it. Then we look for x1 right here, 24.8. So somehow you invest kind of less than a third of the amount on Monday. Then x2, you use $52. x3, $23. x4, $93. x5, 0. Okay, so even though we didn't tell it explicitly that you should not invest on Friday, it figured out itself. You should not invest on Friday. And similarly, you should not invest on Saturday. How could it figure it out? Well, we told them that if you do invest on Friday, you'll get, well, less money on Saturday, but what you want to do is just maximize the amount of money you get on Saturday. So if you increase x5 by any amount, the amount that you get on Saturday will just decrease. So when you get the optimal solution, you automatically figure out that x5 is equal to 0. And similarly, x6 is equal to 0. Okay, let's try to understand the logic behind this schedule. I mean, we got some random numbers. Let's see what other variables can tell. Say E1. So at the end of first evening, you will get $65 left. Okay, not much understanding from here. E2. Okay, this is something interesting. At the end of the second day, you already have 0. So you use up all the amount that you have, so that by the end of the second day, you get 0. You get 0. E3 is equal to 0. E4 is equal to 0. E5 is equal to 0. Well, and E6 is of course not equal to 0. That's the amount that you get on Saturday. So it seems that the logic behind this schedule is as follows. You want somehow to smooth your investments over time in such a way that on every day from, well, not Monday, but Tuesday through Friday, you want to end up on this day with 0 amount of money. So you want to use all the amount available, so you want to plan your investments in such a way that at the end of each of the days, you will get exactly 0. which is kind of reasonable. You don't want kind of to have idle money in your hands. Well, except on Monday. On Monday there is no way to avoid this. Well, mornings, well, I don't really see any pattern to the mornings, so they seem to fluctuate in some kind of fashion. So at least we got this information. If you remember, last time we suggested a 1A strategy, kind of greedy strategy. Try to invest as much as you can so that you'll have enough money to reach it balance on the next day, and then collect the investment on the third day. And our strategy led to objective function of 160. So the obvious kind of greedy strategy that we discussed last time wasn't optimal. In fact, the difference between what we discussed and this one is almost 30, so almost 1/3 of the initial amount of money we had. It does pay to know the optimal solution versus just guess some obvious one. Okay, so we got these numbers. Maybe first, any questions about the solution or the formulation of the problem? So this is the formulation, this is the solution.
What's the interpretation of the reduced cost in this?
Okay, so let's think about this. So reduced costs are associated to some variables. To be honest, not all of those are really meaningful. I mean, they are meaningful in some sense, but let's think about, so the zero numbers are not that interesting to interpret. It means that if you change, if you force let's try to interpret the non-zero numbers. So the non-zero numbers. The reduced cost of E2 happens to be 0.52. What does it mean? So what is reduced cost in general? Recall that it is the kind of shadow price associated to the inequality. The corresponding variable is positive. So it is kind of the loss in the objective function that you will incur if you replace, in this case, E2 is positive by E2 is greater than 1. So if you force E2 to be at least 1, so if you force to end the second day with at least $1, if you are forced to keep some balance in the second day, then you will lose 52 cents in the objective function. So, okay, maybe this way it's not kind of the most interesting information, but let's make it interesting in the following way. Of course, if you replace this E2 is greater than 0 by E2 is greater than -1, what will happen to the objective function? It will increase now. Yes, it will increase. And how much will it increase? By this amount, 52 cents. So if at the end of the second day you will borrow $1 and use it somehow in this problem, you will get an increase in, well, the total profit of 52 cents. So what is this 52? So if you can borrow some amount on day 2, which you will have to kind of return on day 3, because we don't change any other things. We don't change E3, it's still 0 and so on. So if there is an option for you to borrow some amount of money on day 2, how much interest will you be willing to pay for this option? The answer is up to 52%. So let me explain once again. If you replace the amount of the restriction that at the end of day 2 you are forced to have only positive amount of money, E2 is greater or equal than 0 by some kind of borrowed amount. So E2 is greater or equal than, say, -1. You borrow $1. Your profit in the end of the whole week will increase by 52 cents. It means that you are willing to pay up to 52 cents for the privilege to borrow $1 on the second day. So that's exactly the interest rate to which you will agree to borrow. So this amount tells you, you will agree to an interest of up to 52% per day for this option, to borrow on the second day. Similarly for E3, you will agree to much smaller interest, only 13%. 29% on the fourth day, 13% on the fifth day. So somehow, some days are much better for borrowing than other ones. Somehow you can use some amounts much more effectively than others.
Excuse me, how much of the model, would it be possible without changing the entire thing to say, okay, you don't have to pay me back until the last day, still optimize your quantity on Saturday, like, find the interest rate you're looking to pay?
So you can, once again,
If, so, you can borrow to optimize your quantity on Saturday, but say you pay it back Friday night. How much different would this model have to be in order to tell us what interest rate, like what the reduced cost of the entire model is?
okay, I see. So the question is, right now we discussed only what happens if you allow to borrow on the second day, but you'll have to return this amount on the third day, because we don't change E3. And the question was, suppose you allow to borrow on the second day, and to keep this amount actually in play all the way until Friday. How much will you be willing to pay for this option? So unfortunately, this information is not available from just reduced costs. The reduced costs are just about changing one parameter in the model. And here it will be about getting some amount on Tuesday, and then allowing to have borrowed money on Wednesday, Thursday, Friday. Can we?
Do you have to set some, you gave the example of E2 being allowed to be -1. Do you have to set some boundary?
I think that this will be the best solution. So if you want to check what will happen if you allow to borrow on the second day and keep this $1 for the rest of the week, then I believe the best thing you can do is just actually impose these constraints. But now, instead of E2 being greater than 0, you'll impose E2 greater than -1, E3 greater than -1, E4 greater than -1, and so on. So
Okay, so that would be if you wanted to borrow on day 2 and then just borrow on day 2. But what I was really asking was, if you want to borrow on day 2, say you want to also borrow on day 3, say you want to also borrow on day 4.
oh, I see.
But
So I would say that
Actually, if you went E2 greater than -1, it's still the same number. You want E2 to be -1.
what do you mean?
If you just add
Oh, so you just check it on the
Yeah.
computer. The reason is if you write E2 greater than -1, it will still interpret that there is a constraint that E2 is greater than 0. So you will check. This will be just redundant. You'll have also to write something like this E2, the E2 is not supposed to be
Okay.
positive. In this way, you will get what you want. Is back to your question. question would be to go back to this problem, to the formulation of this problem, and just say that there is an extra operation of borrowing. So go back to this table. Data line of borrow B1, B2, B3, B4, B5. Set some bounds on how much we're allowed to borrow, and see how will the end amounts in each day be changed. So we will have to actually change the model a little bit.
Can you not set a bound on how much you have to borrow? Because,
Then you will get probably
but say the fact that you have to pay it back Friday night. So can you not set a bound and then just set a Friday night constraint?
So I'm afraid that no, because I mean, what I will do is just on Monday I'll borrow infinitely much, say 1 billion, use it for 2 days to get 2 billions, return the 1 billion, and we'll keep it until Saturday. So I'll get an unbounded problem.
Right.
I mean, I could have borrowed not 1 billion, 10 billions, 1 trillion, whatever. So if we don't bound it, I mean, only the float operations will keep me from borrowing. So I guess you will have to bound how much. Okay, so maybe back from this question to that question of interpreting this 52 cents as reduced cost. So we said that it is about replacing the inequality E2 is greater or equal than 0 by inequality E2 is greater than -1 and seeing how much the profit will increase. Let's check that this is actually what happens. So I believe that this amount will grow by 52 cents. If I, instead of E2 greater than 0, will write E2 greater than -1. But if I just write it like this, what will happen is nothing changes. You'll see that the objective function is still exactly the same. And in fact, if you look at E2, it is still 0. So the model decided not to borrow anything. The reason is Lindo always interprets any kind of problem as implying that all the variables are positive. If you want the Lindo, if you want this program to think that some variables are not necessarily positive, you'll have to specify it explicitly in the end of the actual problem. So after the line n, you write 3 E2. So this tells you, well, 3 E2 from this constraint that E2 is positive. So 3 E2 is just a pre-number, it can be positive or negative. But now you also impose this constraint that E2 is greater than -1, so you're not afraid that you will get kind of unreasonable answers, unbounded problem. You solve it, and let's see whether we get this 52 cents. Okay, yes. So our objective function increased from what it used to be, 31 cents to 83 cents. So the difference should be exactly 52 cents. And on the second day, you end up with -$1. Maybe another question. What will happen if I allow to borrow quite a lot on the first day? We know that reduced cost is about borrowing, is about changing a constraint by a. What will happen if I allow to borrow $1,000? What's your prediction? What will happen to the objective function? Will it increase by something like 1,000? Will it increase by something smaller, larger?
The reduced cost is 0 now, so.
Yes, so the reduced cost is now 0.
So then to decrease it further than that will happen, right?
So what happens is the reduced cost is a number which is, it is a number which is associated with the constraint EI is greater or equal than 0. If there is no such constraint, they explicitly said there is no constraint,
right.
E2 is greater than 0, It just says, well, there is no reduced cost.
Okay, so it doesn't give you a reduced cost for the minimum that.
No.
Okay.
So now, if you want to look for this number, is about what happens if you replace
Yes.
0 by something, it will get a dual price associated with this constraint. And if you look here, so it should be written somewhere here. So all the constraints are named, but one, the one that we didn't name, and the corresponding dual price, shadow price, is once again 50%. So it still will increase. Okay, back to this question. What will happen in this problem? Would you expect that the objective function will increase by 1000 or something like this? Will you expect it not to increase too much? Will you expect it to increase by 520? Will you expect it to increase more than this, less than this?
Is it just, it's just the interest rate? So 0.52 interest on $1,000 is
Okay, so we can try to check this. So let's try to solve this. Images and see what the objective function is. Okay, it grew by 70, not that much. So somehow you were allowed to borrow as much as you want on the second day, but for some reason, well, it didn't get reflected in increasing the profit on the second day. Why is it? So let's look at these numbers. At the end of the first day, you get, well, you invest everything you have on this first day, the whole $90, because you know you will be able to match this amount from borrowing. So you will be able to match this amount by 45 on the second day from borrowed money. Okay. Then on the second day, for some reason, you borrow not the whole 1000, but only 114. What is the reason? So why wouldn't you borrow 1000 and use the whole 1000 to invest in the second day?
You have to match it.
You have to match it, exactly. So imagine that you use 1000 and invest the whole 1000 the second day. You'll have to match it by something on the third day. But according to this model, at the end of the third day, you can't have any borrowed money. You have to return everything on the third day. So if you use the 1000, you will now have to use another 500s which you can't get. Even if you take something like invest 600 and match it by 300s, well, once again, on the third day, you'll have to return this 1000 that you borrowed. So you don't have this money. So you can only borrow that much on the second day. Then on the third day, you'll return the money that you borrowed. You'll get some return from the first day, corresponding to this amount, and somehow this will actually work. At the end of each other day, you'll get a balance of exactly 0. So this shows that our interpretation of the reduced costs is actually only about small changes. It's not about large changes. Large changes, well, because of some reasons, like here, some constraint about what you have to return, might have some influence which you didn't expect to start with. Okay, let's move back to the original model. So what's good about this implementation is, as I said, it's quite easy to change the model, some parameters in the model. For instance, if you have to measure your investment by not half but 1/4 of your investment on the day before, it's quite easy to do. You have just to change the 0.5 by 0.25. So like this. Then you see, in this way you can get much more by Saturday, because you have to match by less and you still get the whole 2 times X. Another thing, let's say you get 10% interest on your balance that you invest your balance overnight. So whatever amount you get here, you can invest and get 10% more the next day. How will it be reflected in this model? Well, quite easy. You start the next day, not with the amount that you ended the previous day with, but with 1.1 times this amount. So I'll have to change each one of these constraints, to saying that the second morning I get 1.1 times the previous balance and plus the investment. And I'll have to do this for each one of those. So let me solve this. Well, naturally my objective function increased a little bit more, but I still actually didn't use my interest, my option to invest with interest that much. On the first day I did keep some balance, $71, which I probably did invest overnight and got another $7 the next morning. But then, the second day, third day, fourth day, fifth day, and sixth day, sixth day. Fifth day, I got a balance of 0. So it turned out that it was more profitable to me to use up all the amount that I had to invest this amount of money in this opportunity instead of investing it overnight in the bank and getting $10, 10% per day. So this investment opportunity was actually very good for me. What will happen if I can invest at really large interest rate, say 50% per day? Not 10% per day, but 50% per day. What would be expected will be the optimal strategy. So the question is, suppose I change this interest rate from 10% to 50%, like this. Maybe 70%. So something really large. What would you expect the optimal strategy to be now? Just invest in overnight. Yes, it sounds like if the interest is good enough, then I won't just use this opportunity at all. I won't divert my money to some kind of stupid investment like this. I'll just put it in the bank. If it gives me 70% every day, well, I'll just keep it in the bank. Let's see what the actual optimal solution is. X0 is 0, x1 is 0, x2 is 0, x3 is 0, x4 is 0, x5 is 0. So exactly what you said. You invest nothing every day, but you put all the money overnight in the bank account. And of course there should be some kind of transition from one solution to another solution, some interest rate, which will change a decision from using this opportunity to not using it. And that's, we can figure it out. It's not complicated to figure out what this interest is. But unfortunately, you can't do it automatically. You have to think about it and write it down. If you wanted to let this number, the interest rate, to be some variable, you'll get to a problem which is not linear anymore. So you can't say something like this. Let this be some variable interest rate and do something. Such a problem will not be linear. This thing, a variable times a variable, is not a linear function. Linear function is only about a number times a variable. So if you want to figure out what is the interest rate, which is the transition between one strategy and the other one, you'll either have to play with this number, increase it a little bit, decrease it a little bit, and see when you get this transition, or think hard and figure out the exact expression for this number. It's not complicated in this case, but in general, kind of this question of how different parameters in your problem influence the optimal solution in the end, well, some of them are in the domain of linear programming, like how will changing the 0 to 1 will change the optimal function. That's what we can answer. That's about the shadow price of this constraint. Some other parameters, well, not so much. Okay, so maybe any questions about this problem? Okay, so if there are no questions, we can't really start a new topic. We have some interesting questions to discuss here. Maybe back to the original problem.
I have a question.
Yeah.
You know how you said about the interest rate and how much you increase it when it was too much? Can you use the sensitivity analysis to figure that out?
So sensitivity analysis will only tell you what will happen if you increase these numbers or this number. So this number 1. What you wish it could do is what will happen, how much you can increase the coefficients in the matrix, but that's not the sensitivity analysis here. So we'll talk a little bit about coefficients in the matrix and how changing them influences the solution when we discuss sensitivity analysis. I guess week 12, almost in the end. But once again, our tools will not be powerful enough to answer these questions. So I want you to go back to the original problem and try to discuss some shadow prices. So if you go to the shadow prices here, each constraint, well, doesn't have a slack or surplus. Of course, no. It's not an inequality constraint, it's equality constraint. So it must be actual equality, but it still has some dual prices. How much changing the right-hand side from 0 to 1, from 0 to -1, will influence the objective function. What are these dual prices about? In fact, they are, okay, let's think about the dual price of, well, this one is the simplest one. Dual price of the constraint on 1 is 90. what is this dual price? First of all, it is the dual price of morning 1, so it is 2.081. What is the link of this number, 2.008?
Would it be like if you were able to get like an extra dollar on morning 1, you'd be willing to pay 2.08?
Exactly. So it's about what will happen to the objective function if you increase this 90 from 90 to 91. So if you increase it to 91, it tells you that the objective function will grow by approximately $2. So it means that indeed, if you can borrow $1 on the first, sorry, not borrow, rather earn $1, you don't want to return it. It's something that you just get on the first morning and you don't return. So if you manage to, I don't know, find your own $1 in your pocket, how much is it worth to you? Well, this $1 will become $2.08 by the end of the week. So it's worth for you now kind of the same amount as $2 will be worth at the end of the week.
Does the dual prices only work for small changes?
Yes, once again, the dual prices only work for small changes. If you want to figure out how much you can change this 90, how much you can change this 90 for this relation to hold, well, we can either think a little bit, kind of course, if I have twice as much money, I'll get twice as much profit in the end. It won't change the strategy in any way. So it seems that you can change this 90 by as much as you want, or you can run sensitivity analysis. So let's run sensitivity analysis here. How much can you change this 90? Let's go to sensitivity analysis for the right-hand sides. Right-hand side ranges for morning 1, and it tells you infinity. So in fact, you can increase this 90 as much as you want, and the dual price still will reflect what you expect. Well, of course, the dual prices for other variables, morning 2, morning 3, morning 4, are about, well, what kind of thing? If you manage to earn $1 extra on morning, say 3, how much is it worth to you? Well, if on morning 3 you get $1 extra, it will be worth for you 1.56. If you get $1 extra on morning 6, on Saturday, it will be worth exactly $1. So it is reasonable. And similarly about these amounts, they are about how much finding $1 on the evening of this day is worth. Okay, so see you next time. We'll start the new
Wait, was it right?